Good evening, students. Now I'm going to count the topic complex number with some basic properties. In pursuing this chapter, first we have to define the question that why complex number is introduced in real life. Okay, what is the use of this? See, if you get a quadratic equation like this, a square plus 1 0, then you will get a square is equal to minus 1. Now, answer me, does real number system can give us any solution of this type of equation? No. Why? Because in real number system, this result is abstract, imaginary. Why? Because in real number system, there is no perfect square which is equal to minus 1. Then, to explain it, we have to take the concept of complex number, and that is introduced by great mathematician Euler. Okay? What does he explain? That if you get the equation like this, then you will get a negative term minus 1 under root, which is imaginary. Okay, and that will be denoted by imaginary number denoted by I. What is the nomenclature of I? I is iota. Okay, so this is first introduced by mathematician Euler, and he described that if you get any number which is negative under root, that is imaginary number denoted by I, that is called iota. So this is the requirement of complex number. This is the requirement of introduction of complex number in real life. Complex number, this complex number is denoted by script C. Like see, you are quite familiar with, you see, set of natural number. This is set of natural number. You know, this is superset set of whole number, because whole number actually superset of natural number because it contains one element more than natural number, that is 0. Set of integer consists all element of W, so W is the subset of integer. Now real number that is comprising of rational plus irrational, that is real number. And complex number is the superset of all. Complex number is the superset of all set, and it will be denoted by script C. Okay, so any real number also be expressed by the complex form. Now the question is, what is complex form? So I hope you could follow this thing. So I'm grabbing this. Now, in complex plane, a point can be plotted, and like coordinate geometry, a complex plane also has two axes. One is perpendicular on other, like x-axis, and this is y-axis. And the plotting of point will be measured with respect to origin. Now, what is the basic difference of this complex plane with Cartesian plane of real numbers? See, in Cartesian form of real numbers, this x-axis is considered real axis, and this is also real axis. But in complex plane, this x-axis is real axis and y-axis will be called imaginary axis. Okay, imaginary axis. Now, if you consider a point, say A comma B, as you used to consider in coordinate geometry, in complex plane, it will be described by A plus IB. Okay, so a point which is considered in coordinate geometry by this ordered pair AB, in complex number, it will be denoted by A plus IB, where you see A is a real component. See, if you drop a perpendicular, this is X component, this is Y component. A is real, B is also real. But as iota or I is attached with B, so this part I will call imaginary. Okay, this part is called imaginary as I or iota attached with B. So this B is called imaginary. Hope you understood. Now, this A plus IB is the representation of a point or plotting. In this way we can plot a point in complex plane. This complex plane is called argand plane. Argand plane. It is denoted by Z, or you can pronounce it Z. Z is equal to A plus IB. Z is equal to A plus IB is standard form of complex number. This is called standard form of complex number. Suppose any point, if you get 3,2 in coordinate geometry, then what is its representation? Standard representation is complex plane or argand plane. That is Z T plus 2y. Okay. So what we have taught in this short span, that if I plot a point A comma B in coordinate geometry, then in complex plane or argand plane, it will be expressed by A plus IB, where A and B component are real, but as iota is associated or attached with B, so B part is called imaginary. And this representation will be denoted by Z or Z, and this is the standard form of complex number. Okay, and this is called Cartesian standard form or Cartesian form. Standard form of complex number in Cartesian form. Cartesian means in terms of xy. xy. There will be other form of complex number like polar form, Euler form. Okay, but this is the basic Cartesian form, as we got in coordinate geometry also. See A comma B, one is X component, another is Y component. Here also X and Y component. So it is called Cartesian form. Hope you understood. This is the basics of complex number. I'm wrapping now. So, few minutes back, I have told you complex number is the superset of all sets in number system. Say you get a point 2. So can you express it in terms of a complex number? Yes. 2 plus I into 0. That means that real number can be also expressed in terms of a complex number. Okay. So if real part is 2, real part is 2, real part means real component 2 goes along x-axis and imaginary component is 0. 0. That means it, imaginary component 0 means it lies on x-axis only. So this is point in coordinate geometry 2, 0. In complex number, it will be expressed by 2 plus I into 0. Okay, so a real number can be expressed in terms of complex number. So real number is also the subset of complex number. Okay. Now we are going to plot a point on R1 plane. Say a x comma y, that is with respect to x and y axis. Okay. Now if I drop the perpendicular, so this is x component, this is y component. Understood? Now this point is in complex number will be expressed by x plus iy, that is already denoted by z, and you are taught that. Now if I produce it in downwards direction, if you go upwards, the y will be positive, and if you go downwards, this will be negative. So what will be the coordinate of this point? S comma minus y. Now how can you express it by the standard form of complex number? X minus y. So actually this point, say I am leveling the point by P, and that is by P dash. Now this P dash is the mirror image of P, and vice versa. P dash is the mirror image of P, and vice versa. That mirror image is called, conjugate of Z in complex number. This is called conjugate of Z in complex number, and it will be denoted by Z bar. Put a bar sign on the top. That means if Z is x plus iy, then Z bar will be x minus I. So what conclusion I can draw? That if Z is equal to x plus iy, then its conjugate Z bar x minus iy. Okay, and vice versa. I can call that P dash is the mirroring image of P, and vice versa. What is meant by that? That this is the mirror image of P, and P is the mirror image of P. So if you get, if Z bar is equal to x minus iy, then Z double bar, put another bar on this, then you will get back x plus iy as the mirror image. So from this concept, you have got a new property, that Z double bar is equal to Z. Okay. So what is complex number, and what is image, mirror image, and how it is called conjugate, then you have come to know. So I'm rubbing this part, and I'm going to skip to the next topic. See, that part we are taught mirror image. Now that image concept you got even in coordinate geometry. So you have seen that coordinate geometry and complex numbers have so many similarities in properties. Actually, complex number, coordinate geometry, vector, and all these are defined as a point. But see, in complex number, we are getting some extra privilege. We can add 2 points, we can subtract, one point from other, we can multiply 2 points, and we can divide one by other. So all these four properties are held in complex number. Okay, but in vector only addition, multiplication, and subtraction allowed, not division. So complex number gives us one extra privilege. So complex number is one step ahead than vector. Vector one step ahead than coordinate. But all these are interrelated. Okay. Now, so using previous concept, if you get 3, 2 is a point, and the problem is what? Express it by standard form and find its conjugate. So you are quite familiar with this type of problem now. 3, 2, that is a point in coordinate geometry. Now in Argand plane, its expression is z is equal to 3 plus 2i, and its conjugate z bar 3 minus 2i. So this is the mirror image of this, and vice versa means z double bar means if you take the conjugate of this again, means 3 minus 2i is conjugate, that will give you return 3 plus 2i, that is equal to z. So this concept already you have done. Okay, so what is a point and what is a conjugate in Argand plane, we are taught. Okay, so I'm wrapping this part. I hope you understood. So many interesting and important formulas are knocking the door, and I will try to cover up few of them in today's class. See, so you have got zx plus iy, and z bar means conjugate x minus iy. So if you, as I have already told you that in complex number, product of 2 points are allowed. So you multiply z into z bar and see the outcome. X plus iy into x minus iy. So what formula does it follow? You are taught in your junior class, a plus b, a minus b, a square minus iy whole square. So z into z bar, a square, I square, y square. What is I? At the beginning of the class, I have told I or iota is equal to root minus 1. So I square is minus 1. Put there. So you will get a square plus y square. Now the question is, in this result, in this derived result, are you finding any I? The term iota? No. So this will not be considered as a imaginary or complex number. So this is a real number. This is a real number as I is absent in this expression. Therefore, a complex number and its product and its conjugates product is always real. A complex number and its conjugates product is always real. See, this is a basic level property, interesting, okay? But if you don't get, the chapter will be out of your grip. But this is an important chapter, even in joint entrance, IIT, engineering, higher mathematics, BSc, MSc. Okay, so this is if you don't go through this basic level, complex number property, then you will get a tough life in higher study. So this part is understood. Now, what is the use? How, where I can use this property? Let us take one example to make you understand the use of this property. I'm rubbing this part. See, suppose you have got 1 by 2 plus 3i, and you are told to express it by its standard form. What is the standard form? Standard form is a plus ib or x plus iy form. But here, x plus iy or a plus ib, I have got it in numerator denominator. So I have to remove I from denominator. How? We have come to know in the previous theorem that if a complex number is multiplied by its conjugate, then the product will give you real. So how to remove this I from denominator? What is the mechanism? The mechanism is that you have to multiply the denominator's complex expression by its conjugate to bring a real number. See, 2 plus 3i, its conjugate is 2 minus 3i. So you multiply 2 minus 3i in numerator and denominator. It results what? 2 minus 3i, 2 square, 3i whole square. That gives you 2 minus 3i, 4 minus 9i square. What does I square means? You are quite familiar. Now it is not a new concept for you. 2 minus 3i, 4i square is minus 1, so 4 plus 9. That means 2 minus 3i by 13. So express it with the standard form, split up 2 by 13 plus minus 3 by 13i. So at last, we are able to express this complex number in its standard form. Okay, so here you can use that concept of product of a complex number and its conjugate. Understood? So I'm rubbing this part. Now, a concept will be built up whose semblance you got in real number system. You know, in a right angle triangle, if perpendicular and base is given, then you can get hypotenuse. In real number system, you got Pythagoras theorem to get the hypotenuse. Pythagoras, axioms. Actually, it is not the exact theorem, segment of the theorem. The perpendicular square plus base square is equal to hypotenuse square. Now, how it is related to complex plane event? See, draw the Albert plane again, and you take a point xy. X is x component along horizontal or x-axis, real axis that is, and y is, a y component along y-axis. Now, this is x component, y component. Okay. Now, if you join this point to the origin, then you will get the length x square plus y square, and that is called modulus of z, which was considered as hypotenuse in a right angle triangle in Euclid geometry. See, if z is equal to x plus iy, then see, this is also a right angle triangle. The hypotenuse of a right angle triangle is considered as modulus z. modulus of z in argand plane, So mod of z will be root over of x square plus y square. Symbolically, it is denoted by the z confined into vertical line, and by definition it is called modulus of z, and in short I can write mod z. So the mod z is root over of x square plus y square, and in finding mod z we will take x component and y component, the real part, not the imaginary part. Okay, length cannot be abstract or imaginary. So if you get z is equal to 3 plus 2y, then his modulus will be 3 square plus 2 square, that is root 30. In vector it is called magnitude. Okay, scalar value. Understand? Scalar value. So this is called modulus of z. Hope you have no problem in accepting this. Now, from this concept, we can derive another property. What property? Few minutes back, we are taught z into z bar is x square plus y square. So, from the basic concept of the yesteryears, we can write x square plus y square as root x square plus y square whole square. And just now we have come to know this is nothing but mod z. So z into z bar is nothing but mod z whole square. Understand? So mod z is a real number. It is not a complex number. It is a real number. It is a length. Okay, so z into z bar is equal to mod z whole square. A new property. The highlighted part will be considered as a property. Okay, so up to this stage, hope there is no problem. Now, let us skip to the next topic. I'm wrapping this part. See, again, let's draw the argand plane. This is the argand plane, and see, this is z, the point in complex plane. This is x-axis, this is y-axis, and point in the complex plane will be expressed by standard form x plus iy. Now drop a perpendicular and stretch it downwards, and this will be, as this was x comma y, means this is x component, this is y component. So this is x comma minus y, and you are quite familiar with the term x minus iy, that is already taught conjugate. Okay, now you got the concept of mod z few minutes back. Mod z is equal to root over of x square plus y square. So what is mod z bar? Mod z bar is what? This x minus iy also can be expressed with the standard form x into minus I, x plus I into minus y. So x square plus minus y whole square, and this minus will be absorbed. You will get back the same value which mod z had. So one conclusion I can draw, that mod z bar is nothing but mod z. That means, see, if you get the length of x comma y from the origin is root x square plus y square, and then the length of x comma minus y from the origin, it will remain same. Okay, so the length of what I can say, this is hypotenuse, or that movement in diagonal does not depend on the coordinate geometry, does not depend on the component of Cartesian form. Okay, it will always remain plus. So mod z bar is equal to mod z. A new concept you have got. Hope you understood. See, if you get, say, z is equal to x plus iy and z bar x minus iy, if I add z plus z bar will give you twice x. Twice x means real part, twice real part of z. This is x is real part of z because that is actually independent of I. There is no I with x. And you could have subtracted the second one from first. Then z minus z bar would have been what? 2iy. That therefore twice imaginary z. That is in short, that is called imj. So z plus z bar is twice real z. Z minus z bar is twice imj or imaginary z. Hope this is not so tough thing for you. It's a interesting and the the knowledge or the depth of this chapter, which is unfathomable. And obviously, if we proceed, gradually. We are not in a hurry. Gradually, step by step, with considering few simple examples, then you can reach that height. You can reach that height. You can touch the depth of this chapter. Okay. So, two conclusion I can draw: mod z is equal to root x square plus y square, and mod z bar is the same. So mod z is equal to mod z bar, and z plus z bar is equal to twice real z, and z minus z bar is equal to twice imaginary z. Okay. So till now we are talking about the Cartesian form of complex number. What other form is there? Now I will introduce a new form which actually includes the radius and the angle made by the radius with the horizontal axis, positive direction of x-axis. That is called polar form of a complex number. Polar form. I'm wrapping this part. Now I will discuss the polar form of a complex number. Polar form of a complex number. What is polar form? See, let us draw the Argand diagram. Any point xy is plotted here, confined here. This is x dash, y dash. Okay, this part is called R. That is nothing but mod z, and mod z is root over of x square plus y square. You are already done. Now this R makes angle theta with positive direction of x-axis. Okay, R makes angle theta with positive direction of x-axis. Okay. Now this theta is called argument of z or amplitude of z. Okay. In short, argz. Now the question is how to convert this Cartesian form of a complex number into polar form and how to find the argument. See, if this is x and this is y, cos theta is equal to x by y, which implies x by r, which implies x is equal to r cos theta, and sin theta is equal to y by r, which implies y is equal to r sin theta. Then what is the standard expression of complex number. Standard expression of complex number z x plus iy. What is x now? You put here r cos theta plus I r sin theta. Okay. Now, what can I take common from here? R cos theta plus I sin theta. This is called polar form of a complex number, where R is mod z and theta is called argument of z. Okay, this is the polar form. Okay, polar form means r theta. Cartesian xy, it depends on x and y component. This depends on radius and the positive angle made by the r with positive direction of x. Okay, so this is called polar form of a complex number, where r is mod z and theta is argument of z. Now, what is the principal value of argument of z? Okay, I'm wrapping this part. Let us discuss about the principal value. What is principal value? Principal value of argument of z. Important part, conceptual part. See, let's draw the complex plane. See, argument of z is theta. Now, if you rotate an angle anticlockwise, then it will move from here on real axis. Anticlockwise means it is positive direction, means angle is measured with positive direction of x-axis. Now, this is measured from 0 to pi. Okay, 0 to pi means here theta lies between 0 to pi. If you rotate in clockwise, then minus pi to 0. How can it be possible? How can it be possible that theta at a time equal to pi or minus pi? So you exclude the minimum value of theta, that is minus pi, but include plus pi. Combine them. Pi to 0, 0 to minus pi, but minus pi will be excluded because already I have equaled theta with pi. Once you equate theta with pi, then it cannot be equal to minus pi. So I have excluded here strictly less than theta strictly greater than minus pi. So this is the principal value of theta, or principal value of arg z. Okay. So whatever be the value of argument z means so many values. It can be 0. Suppose any point lying on x-axis. Okay, lying on x-axis. Then it can be 0. It is 0. If you give 2 pi rotation, then plus 2 pi. In clockwise rotation, minus 2 pi. Plus minus 4 pi. So whatever you give, all lies between minus pi to plus pi in this interval. That is principal. Okay. So if you are told to find the argument of z, then you have to examine that in what the point lies, and it satisfies the interval of principal value or not. Okay. Let's take one point, say 1 comma minus 1, 1 comma minus 1, and you are told to find its polar form, and first you are told to find the argument of z. Okay. Now first you express this in terms of standard form 1 plus minus 1 into I. Now 1 is considered as r cos theta, minus 1 is considered as r sin theta. Now in these two equations, r and theta are known. How to make r known? Square and add. 1 square plus minus 1 whole square is equal to r square. R is equal to root 2. We have got r and divide it. You will get tan theta is equal to minus 1. Tan theta is equal to minus 1. Now examine that 1 comma minus 1 lies where? 1 minus 1 lies in the fourth quadrant. So in what manner you will take the argument of z? If you take anti-clockwise rotation, means this 2 pi minus theta, okay? 2 pi minus theta. You can take this angle, you see 2 pi, pi by 2 and something. But see, it crosses that limit. So you take 2 pi minus theta, okay? So see, minus tan pi by 4 means it is taken in anti-clockwise rotation. See, minus tan pi by 4 means tan of minus pi by 4. So theta can be minus pi by 4. Okay, it is considered here theta is minus pi by 4. Does it satisfy this interval? Yes. So this is argument of z. But someone can say, okay, if I write 2 pi minus theta, because minus tan pi by 4, minus tan pi by 4 can be tan theta tan 2 pi minus pi by 4, but that will give you tan 7 pi by 4, theta 7 pi by 4. So 7 pi by 4 is also an argument. But out of these two, what to be chosen? Then you have to examine the interval where theta lies. Theta strictly lies between, principal value strictly lies between minus pi to pi. So 7 pi will not be there. It is exceeding the limit of pi. So I will take minus pi by 4. So don't be confused. Don't be confused. Someone, those who are not considering the interval of principal value of theta or argument of z, they will choose 7 pi by 4, and those who are considering the interval, and that is the valid interval, maximum valid interval, so that they will choose minus pi by 4. This is the correct answer because it satisfies the interval of principal. So this is the way you can find the argument of z. Hope you understood. I'm running and going to skip to the next part. So if you take any point on the first quadrant, and this is theta, so this is the argument of z in first quadrant. If you get the angle like this, you can take what? Pi and go anti-clockwise, then minus pi by 4 clockwise. So this is pi minus theta. This is argument of z. This is argument of z. Argument of z in second quadrant. Now, if you skip to the third quadrant, like this, if you take 2 pi plus theta, that is also right. But this 2 pi plus theta does not belong to minus pi to pi, that interval. This is the principal value of arc z. So this is not the arc z in third quadrant. Then how to count? How to find it? Take minus pi means clockwise in In third quadrant, argument z is minus pi plus theta. Okay, minus pi plus theta. And what about in fourth quadrant? Suppose here you get, okay, in fourth quadrant you are just thought that actually if you give 2 pi rotation anti-clockwise minus theta, but then you have to examine that whether that will satisfy that interval or not. Okay, so better you take in this way, either minus theta or 2 pi minus theta as the argument. Okay, these are the argument in different quadrants, and that will play an important role. Okay, so I'm rubbing this part. You are taught what is argument, and see what is the, see if you get z is equal to r cos theta plus I sin theta, then r is nothing but mod z, and cos theta plus I sin theta, where theta is argument of z. How to find it? See, x is equal to r cos theta you got by the substitution, that is r sin theta divide y by x tan theta, theta will be tan inverse y by x. So this is the, okay, argument of z, where principal value of argument of z lies between, okay, minus pi to pi. That is the principal value, and it will play an important role in joint entrance level exam. Hope you understood. So that converting from Cartesian form to polar form we are taught. Okay, now one example you see, suppose you have got convert minus 1 to 1 to its polar form. First of all, this minus 1 to 1 will be expressed by standard form, z is equal to minus 1 plus I into 1. Now you see here r is equal to root minus 1 square plus 1 square root 2. That is a well-known property. X is equal to, x means here minus 1 r cos theta, y is equal to r sin theta. That conventional substitution, you know, divide it, you will get tan theta is equal to minus 1. Now, how to find theta? First of all, tan theta is equal to minus tan pi by 4. So, should I take this minus inside? Then you have to say, examine that this point minus 1 comma 1 lies where? In second quadrant. In second quadrant, and few minutes back we are taught that pi minus theta is the argument of z in second quadrant. So you can write pi minus pi by 4, that means 3 pi by 4 theta. Okay, so 3 pi by 4, it lies between 3 pi by 4 lies between pi to minus pi by pi to minus pi. So this is the argument of z. So we are able to convert, we'll be able to convert it to the polar form. Z is equal to root 2 cos 3 pi by 4 I sin 3 pi by 4. So this is one important part of conversion from Cartesian to polar form we are taught. So students, today we have covered complex number is the widerness of its knowledge is unfathomable, what I have told few minutes back. So in this short span, we don't have any yardstick to measure the depth of this chapter. So we could touch the basics of two properties, the preliminary two properties of complex number. In next video, I try to give you some more properties that will open so many branches, so many lucrative branches in mathematics, and see few questions which you have not got in real number system will be opened in complex number system. So next day we'll bring some more discussion with some more interesting topic in complex number, and no more today because it is a new chapter. You are doing first time in life, so if I put all together in one video, it will become misnomer. Okay, so better to pursue the later part or other part in next video. Till then, goodbye, good night, thank you.